Think about the last time you booked a flight. Or maybe you tried to track down a really specific kind of obscure item online.
Oh, yeah, like hunting for a needle in a digital haystack.
Exactly. You already know the drill. You probably had to navigate this huge barrage of newsletter pop-ups or, confusing out-of-stock notices.
Right.
And those weirdly designed drop-down menus, and maybe one of those counter TTCHAs asking you to identify, like, every single image with a crosswalk.
Oh, I hate those.
Right. But you handled it, probably while sipping your coffee, not even thinking much about the sheer cognitive load required to actually do that.
Because for humans, that adaptability is just second nature.
Yeah, totally. Now, imagine asking an AI assistant to do that for you. I mean, it sounds like the ultimate luxury, right? An assistant that handles all the tedious digital errands.
It does sound great.
But historically, the moment that live web page changes unexpectedly, like, say, a checkout button moves down just a few pixels, or a promotional banner takes over the entire screen, the AI completely loses its footing.
Yeah, the models essentially suffer a system shock. I mean, they are trained for a very specific digital landscape.
Right.
And when that environment shifts even slightly, the AI just forgets how to navigate. It clicks on empty space, it gets stuck in a loop, and, well, the task just completely fails.
Which is incredibly frustrating if you are relying on that tool.
Mm-hmm.
But what if we could train an AI to surf the live, chaotic internet exactly like you or I do?
Mm-hmm.
Just adapting on the fly.
That is the dream scenario.
And today, we are digging into a cutting-edge research paper that tackles exactly that. It's titled OpenWebRL, Demystifying Online Multi-Turn Reinforcement Learning for Visual Web Agents. This research was put together by teams at UIUC and Microsoft.
And it really represents a profound shift in methodology. I mean, they are proposing a completely different way to teach AI how to navigate the web.
Yeah.
They're discarding the heavy, data-intensive methods of the past and using just a fraction of the computing power to achieve something significantly more adaptable.
Okay, let's unpack this. Because to truly appreciate why OpenWebRL is such a massive breakthrough, we need to examine the friction that's holding back current AI from doing your basic online shopping.
For sure. If you look at the current state of open source web agents, the standard approach relies on something called supervised fine-tuning, or SFT.
SFT, right.
Yeah. And to put it simply, developers feed the AI massive datasets of curated, static web trajectories.
Static, meaning like unchanging.
Exactly. Think of these trajectories as step-by-step screenshots of a human completing a task on a website, accompanied by the exact coordinates of where the human clicked.
So it's essentially a giant, tedious flipbook. A human has to go to Amazon, take a screenshot, click search, log the exact coordinate of that click, take out a screenshot, type shoes, log those keystrokes, and so on.
Yeah, that is the grim reality of data collection in this field right now.
Wow.
For instance, a leading open source model called MulmoWeb relies on over 278,000 of these static trajectories.
278,000.
Yes, and building a data set like that requires just an immense amount of human labor. It is incredibly expensive and time-consuming. You are essentially paying humans to meticulously document their every micro movement on the web.
I mean, to put that in perspective for the listener, trying to teach an AI to browse the internet this way is it's like trying to learn how to drive a car in a bustling, chaotic city by only looking at a textbook of photographs.
That is a perfect analogy.
You study a picture of a stop sign, you memorize a picture of a crosswalk. But what happens when you're actually behind the wheel and a pedestrian unexpectedly steps out from between two parked cars? The photograph didn't prepare you for the dynamic variable.
Exactly. That driving analogy captures the core failure point of SFT. The live web is non-stationary. It does not sit still.
It's always changing.
Right. Websites update their layouts daily to run A/B tests. A pop-up asks for your email address out of nowhere. Or, a network error delays the loading of a page by 3 seconds.
Yeah, that happens to me all the time.
And a static data set, no matter how large those 278,000 examples are, it cannot teach an AI how to recover when the button it wants to click shifts 2 inches to the left just because a video ad loaded at the top of the screen.
The AI just blindly clicks the coordinate where the button used to be, and the whole operation crashes.
Exactly. This raises an important question. How do we train an AI on a web that refuses to sit still?
Right. If textbook learning fails when the environment is constantly changing, you kind of have to put the AI behind the wheel on the live internet.
And that's what they did. They moved away from supervised fine-tuning and proposed a radical shift toward online multi-turn reinforcement learning, or RL.
Okay, reinforcement learning.
Yeah, the strategy is to let the AI learn by interacting with the real thing. Instead of feeding the model those 278,000 static examples, OpenWebRL starts with a tiny supervised warm start. They only use 400 trajectories,
Wait.
just 0.4K.
Only 400 examples. I mean, that feels like giving a teenager a 10-minute lecture on the concept of an engine and then tossing them the keys to a sports car on the highway.
It does sound a bit reckless, doesn't it?
Yeah. If you only give an AI 400 examples of how to use the internet, doesn't the browser just crash immediately when you let it loose?
The instinct is to assume more data equals more capability. But this taps into a crucial concept in machine learning known as plasticity.
Okay.
When you overtrain an AI with hundreds of thousands of rigid, step-by-step examples, it actually loses its ability to adapt.
Oh, interesting.
Yeah, it becomes rigid. It ends up memorizing paths rather than learning concepts. Those 400 examples in OpenWebRL aren't meant to teach the AI everything about the internet.
So what are they for then?
They are just there to give the AI a baseline competence, basically teaching it the 13 atomic tools it is allowed to use in the browser.
Let's define atomic tools for the listener. We're talking about the absolute baseline actions, right?
Right. Basic, indivisible actions. Things like click, hover, write, scroll, press keys, and go back.
Just the mechanics of browsing?
Exactly. By giving the AI just enough knowledge to use these 13 tools, it can explore productively without being locked into a pre-programmed path.
I see.
And once it has that basic toolkit from the 400 examples, the training wheels come off. The researchers unleash the AI on 2,200 live, open-ended tasks on the real internet. It learns purely from trial and error.
Which mirrors human learning perfectly, if you think about
Oh,
it.
absolutely.
When a website you use every day updates its interface overnight, you don't go read a manual or look at a textbook of screenshots. You just, click around.
You explore.
Yeah, you see what happens. Maybe you navigate to the wrong page, you hit the back button, you adjust. You figure it out by doing it.
Learning through interaction and consequence is the fundamental mechanism of reinforcement learning. The AI takes an action, observes the result on the live web, and updates its understanding of how to achieve its goal.
But driving around the live web creates a massive new architectural problem, which is data overload.
Oh, a huge problem.
Right, because if I ask the AI to buy a specific sofa, and it takes 30 clicks, hovers, and scrolls to find it, apply the right filters, and put it in the cart, how does a relatively small AI model process 30 full-page screenshots without its working memory just entirely overflowing?
Right. This is the context management problem, and it is a severe bottleneck in visual AI.
Yeah, images are heavy.
Very heavy. Every screenshot you feed into a model takes up a lot of space. Visual data is converted into thousands of tokens, which is the unit of memory models used to process information.
Okay.
If you stack 30 high-resolution screenshots in the model's context window, it runs out of processing space. It's very much like your computer slowing down when you have too many heavy applications running at once.
So how did they fix that?
The researchers made a highly unconventional design choice here. They programmed the system to just throw away the old screenshots.
Wait, what? Here's where it gets really interesting. How is the AI not flying completely blind? If it just forgets what it looked at 2 seconds ago, how does it know what it's trying to accomplish, or even what it already tried?
It's clever. It replaces that heavy visual data with lightweight text data.
Okay, text is much lighter.
Exactly. The agent keeps something called textual environment feedback. Instead of saving a giant image file to remember what happened after a click, the environment is programmed to hand the agent a short text string.
Like a summary.
Yeah, it says something like, you clicked the search button and the page navigated to a new URL, or you tried to scroll but the page didn't move because you are already at the bottom.
Oh, that's wild. So it's like having a co-pilot verbalizing what your actions just did. It saves you from having to constantly stare in the rearview mirror to verify your last move.
Precisely. And furthermore, the agent also generates its own historical reasoning traces.
Historical reasoning traces.
Yeah, it actively writes down an internal monologue. This acts as a compact, text-based memory of its past actions, its goals, and its mistakes.
Like a diary.
Yes. It might record, I tried clicking the sort my price button, but a pop-up blocked it, so I need to close the pop-up first.
Keeping a diary instead of a massive photo album. That makes so much sense. That saves a ridiculous amount of memory, freeing up the model to actually think about the next step instead of just holding on to the past.
And we know this specific mechanism is critical because of how the researchers conducted their ablation study.
An ablation study for the listener is where you take pieces away to see what breaks,
Yep,
right?
exactly. In machine learning, an ablation study systematically removes components of a system to measure their individual impact. When they removed these textual reasoning traces, essentially wiping the AI's diary, the performance plummeted.
How badly?
It dropped by up to 23.7 points on the online Mind2 web benchmark.
Wow.
And that benchmark is the standard test for evaluating these web agents.
That drop proves the AI absolutely needs that ongoing narrative to function. It can't just react to the current screen. It has to maintain a storyline of its mission.
And what might surprise you even more is what happened when they tried giving the AI more visual data.
Oh, really?
Yeah, they ran a test where they fed the AI the 2 most recent screenshots instead of just one, assuming more visual context would help.
Right, you'd think seeing the last 2 steps would be better.
It actually degraded performance.
Really?
Yeah, and it slowed down training. Beyond the immediate visual frame, the AI gets more signal from its text-based memory of the plan than it does from the noise of extra pictures.
Okay, so the AI is stumbling around the live web, trying to buy a sofa. It's managing its memory efficiently by tossing out old screenshots and relying on its text diary. It's trying different strategies to bypass pop-ups.
Right?
But at the end of the day, how does the system actually score? Whether the AI succeeded or just bought a totally different wrong item? I mean, on the open web, who is actually grading the test?
This is where we get into the trajectory judge and a specific training technique called multi-turn GRPO.
GRPO.
Group Relative Policy Optimization.
Okay, got it.
In traditional supervised learning, the AI is micromanaged. It is graded on every single step, like did you click the exact right pixel? No. Penalty.
Which is super rigid.
Very. But with GRPO on the live web, the AI is graded at the very end of the entire trajectory.
Oh, I see. It's evaluated on the outcome, not the specific path it took to get there. Like, did you actually get the sofa in the cart?
Exactly.
Yeah.
And the group relative part of GRPO is the key here. The AI is asked to attempt the same task multiple times, generating a group of different trajectories.
Different attempts at the same goal.
Yes. Maybe in one attempt it uses the search bar, and in another it tries navigating through the category menus. The system then evaluates the final outcome of each attempt relative to the others. The AI basically asks itself which of these strategies actually got the item in the cart fastest without failing. The successful strategies are reinforced, and the failing ones are penalized.
But evaluating thousands of open-ended tasks multiple times sounds like it would require massive computational oversight. I mean, usually researchers have to plug into massive proprietary models like GPT-4 to act as the judge for every single run, checking if the item in the cart actually matches the prompt.
Right, they use it as an automated grader.
That API bill must be astronomical.
It is. Using GPT-4 as a judge for a standard training run costs roughly $545.50 per experiment.
Ouch.
Yeah, and if you are running hundreds of experiments to refine the model, that quickly becomes prohibitive for open source researchers. So the team solved this by distilling their own 8 billion parameter judge model.
Distilling it.
Yeah, model distillation is a process where you use a massive, expensive model, the teacher, to grade a huge set of data just once. Then you train a much smaller, cheaper model, the student, to mimic the teacher's grading patterns.
Okay, so you essentially capture the giant model's judgment capabilities and squeeze them into a small, open-source model that you can run locally for free. That cuts the cost of the training itself drastically.
It really democratizes the research.
I want to look at the specific trajectories from the paper now, because seeing the AI actually think its way through a problem makes this so concrete. The IKEA sofa example really stood out to me.
Oh, that's a great one. The mechanics of that interaction show exactly why RL outperforms static learning.
So the task the user gives the AI is find the cheapest black leather sofa with at least 3 seats and a 4+ star rating.
Pretty specific.
Yeah, very specific. And the AI navigates the filters on the IKEA site, but then it hovers over a promising item and realizes, based on the text pop-up, that it isn't actually leather.
Right.
Now, instead of just giving up or adding it to the cart anyway, it goes back to the search, it tries a different approach, finds the Freeton sleeper sofa, and then explicitly verifies all the specs.
It checks the list.
Yeah, it checks black, leather, 3 seats, right? Good rating. And then it adds it to the cart. It course-corrected in real time.
What's fascinating here is that the AI didn't check the material because a human hard-coded a rule saying always check the material of sofas.
Right, there's no code for that.
Exactly. It did it because through that GRPO trial and error, It learned that verifying constraints prevents it from failing the final grading stage. It developed a survival mechanism.
That is amazing. There's another example with Birkenstock clogs that I loved.
Oh, the missing button one?
Yeah. The prompt was to look for top-selling men's brown clogs, size 10 to 10.5. The AI gets to the site, but encounters a missing best sellers sort option.
Yeah.
The button just literally isn't there on the live site that day.
And a static trained AI, expecting that button based on its 278,000 screenshots, it would just freeze and fail the task immediately.
Right, because it doesn't know what else to do.
Yeah.
But OpenWebRL diagnoses the issue. It realizes the button is missing, adapts by scrolling around, explores alternative filters to find popular items, finds the right brown clogs in the right size, and successfully completes the task.
This behavior is exactly why the researchers were able to categorize 4 specific human-like reasoning patterns that the AI naturally developed just to survive the live web.
Just from trial and error.
Yes, these are proxies for advanced reasoning.
I can actually guess some of these based on my own frustrating experiences shopping online. Like, when I hit a dead end, my first instinct is usually to retrace my steps or just refresh the page and try a completely different search term.
And that maps perfectly to 2 of the proxies they identified. The researchers call that retry plan loops, where the AI decides to abandon a failing path and try a different search query.
Okay, that's one.
They also identified history summarization, where the AI literally lists its past failed attempts in its text diary so it doesn't repeat them.
That is so smart. What happens when it hits something it simply cannot bypass, though? Like a EP268 or a totally broken link?
That is the 3rd proxy. They call it blocker diagnosis.
Blocker diagnosis.
Yeah. The AI recognizes when it hits a wall, like a 403 error, and explicitly notes it in its reasoning trace rather than just clicking the same dead link over and over.
Which is something a lot of older bots would just do endlessly.
Exactly. And the 4th proxy is condition proof, which we saw in the IKEA example.
Right, the checklist.
It explicitly checks off the user's constraints one by one in its diary. Is it black? Yes. Is it leather? Yes. Is it 3 seats? Yes.
It's basically talking itself through the problem to ensure it gets the final reward.
It really is.
And the results of deploying this method are just a total David versus Goliath scenario. We are talking about OpenWebRL 4B.
A tiny model.
A tiny model with only 4 billion parameters. I mean, in the current landscape of AI, 4 billion is practically a pocket calculator compared to the massive data centers required for the giants.
It is exceptionally small, designed specifically for efficiency.
Yet this tiny model achieved a 67% success rate on the online Mind2 web benchmark and a 64% on DeepShot.
Those are incredible numbers.
Yeah. It completely crushed massive open models, like Qwen 3, which boasts 235 billion parameters.
That's really staggering.
And it didn't just beat the open models, it rivaled the proprietary giants like GPT-5 and Gemini's computer use agents, which have vastly more resources behind them.
Achieving those numbers with a fraction of the parameters and a fraction of the training data fundamentally challenges the current industry narrative.
Ooh, cool.
It proves that throwing exponentially more data and more raw compute at a problem isn't always the necessary path forward. A smarter, more interactive training environment yields a more capable agent.
So let's bring this all together. By combining a tiny warm start of just 400 examples to teach basic tools, using a smart text-based diary instead of hoarding heavy screenshots, and letting the AI actually learn by exploring the messy web and getting graded purely on the outcome.
It's a brilliant recipe.
OpenWebRL proves that massive data hoarding isn't the only way to build a genius web agent. Small, highly efficient models can compete with the absolute giants.
The implications for how we build and deploy AI are just massive.
So what does this all mean for you, the listener? It means highly capable, truly open source AI assistants that can navigate the web for you. Booking those complicated flights, hunting down those specific shoes across 10 different retailers are closer to reality and significantly cheaper to build than anyone anticipated.
Yes.
You won't need access to a trillion-dollar company's supercomputer to run them.
And stepping back to look at the broader horizon, this research leaves us with a really provocative question to consider.
Okay, let's hear it.
If a relatively tiny AI model can learn to navigate the incredibly complex, unpredictable human digital world of the open web purely through interacting, making mistakes, and receiving a final grade,
Right.
what other complex, messy human systems could small models master?
Oh, wow. Like what?
Well, could we see this methodology applied to navigating global supply chain logistics? Or perhaps deciphering and adapting to shifting legal codes in real time. If an AI can learn simply by being allowed to participate and fail in an environment, rather than just studying a static map of it, the potential applications extend far beyond browser automation.
It really makes you wonder what other breakthroughs are waiting once we stop trying to teach AI with static pictures and just hand it the keys to the environment.
The sky's the limit.
We want to thank you for joining us on this deep dive. Keep questioning the systems and the information around you. And, next time you find yourself clicking through a terrible, broken drop-down menu, just remember, pretty soon, you might be able to hand that headache over to an AI, let it do the driving, and avoid the digital traffic altogether.